So this is continuing again, chapter 15, equilibrium. I'm going to work a couple problems here so you could kind of see how to apply some of this. So we have two reactions here, the process of making sulfuric acid, and they're both at equilibriums and they're all gases. So I'd like you to write the expression for K for each reaction, and we're going to do Kp. This is an old style AP question. So again, please note, oh, there is a solid in that first reaction. Please note that it will specify whether you want a Kp or a Kc. So here's your expressions. Again, you're just taking the fact that you have a solid in that first equation, so you don't include it, and you write pressure in parentheses as you do. So part B, okay, this part may not make a lot of sense at this point, but it'll make a little bit more sense as we get into the last part of equilibrium. At 900 degrees Celsius, the Kp for the reaction 2 is 6.5. At 1,000, the value goes down to 1.86. Is the reaction endothermic or exothermic? Explain your answer. So what is happening is, as I am increasing temperature, okay, the temperature is going from 900 to 1,000, my K is going down. Well, if your K is going down, that means your reactants, okay, are increasing. Okay, so this bottom number is getting bigger because the K is getting smaller. So understanding the math behind it might help you. So if I have my second reaction, reactants going to products, okay, just to simplify it a little bit, okay. If I am producing more reactants, okay, that means it's going towards the left. And if I'm increasing temperature, I'm essentially increasing the heat. So if I'm shifting it towards the left, that means the heat must be on my product side. So that is what we call a traditional exothermic reaction. So we're going to be talking about shifting reactions here in a couple videos from now. So if this doesn't make quite a bit of sense, it'll make a little bit more sense going forward. But I also like to show you that the K does change with temperature. There is a calculation we could do. There is no calculation on the AP test about the K values, but you can actually calculate a different K at a different temperature. Instead, I want you to focus on what is happening to the K when you change temperature. All right, so part C, what is the value of Kp? Well, Kp at 1,000 for this reaction. Well, realize that this reaction is essentially this second reaction. Oops, let me bring it down. This second reaction, but what has happened is I have flipped it, so the SO3 is over here, and I've also doubled it, okay? So I'm going to use this value at 1,000 of 1.86. So what I'm going to take is 1 over 1.86, but I also square it because I doubled everything. So this is going back to when we talked about the K's and what we could do to it. So 0.289 is what you end up with at that new temperature. And then what is the value of Kc for the reaction 2 at 1,000? So again, we know Kp is equal to Kc times R times T to the power of the change in N. So my Kp value at 1,000 is 1.86. I don't know my Kc, but I do know, and we're going to do this in atmospheres, and again, I would tell you that. And then my temperature is 1273 Kelvin. But the question mark is, what's my delta N? So if I go back to this equation here, I have 1 mole on the product side, and I have 1.5 on the reactant side. So that means this is brought to the -1/2 as my power, okay? So when you do the math, the Kc turns out to be about 19. Right? So that kind of involves, again, some of the calculations we've been talking about for K. All right, so this next problem on the next page, sodium bicarbonate can be decomposed with heat to make sodium carbonate, carbon dioxide, and water. If a sample is placed in an empty flask and reaches equilibrium at 100 degrees Celsius, find the total gas pressure at equilibrium if the Kp is 0.23. So why don't you try that? I'm going to come back on and show you the answer. So recognizing the only two gases you have here are the carbon dioxide and the water. So I know that each one of those are in a one-to-one fashion. This would all not be part of the equilibrium because they're solids. So that would mean if I'm starting with the solid, these would start at 0 and they would go up by a factor of x. So I take x times x, which gives me x squared. So mathematically, I got to take the square root of the Kp to find my x, which comes out to be about 0.48 atmospheres. But what it's asking for is the total gas pressure at equilibrium. Well, realize I have CO2 and I have water in there, and they're both going to be 0.48. So my total pressure, so this is total pressure, is 0.96 atmospheres. All right, so the next one is far more interesting. It kind of gets at a couple different things that we've been talking about. So N2 plus O2 goes to 2NO. My Kc is this at 2130 degrees Celsius, and it's telling me my delta H is 0, or excuse me, greater than 0. So that must mean this is endothermic. So endothermic again means heat is on the reactant side. So I'm going to write it over here. In a 1 liter containers, combine 1 mole of nitrogen, oxygen, and NO. At that temperature, what happens? All right, well, recognize that the temperature is not exactly the same, but we can still find some information. So when it asks what happens, think Q. Think Q. So I have all of the concentrations of each one of these. Now, I could take this as I'm going to do this as moles, and I'll explain why I could do that. So I have 0.2 moles on the top, and that's going to be squared. And on the bottom is 1 mole and 16 moles. Now the reason I could do that is because I have equal amounts of reactant in terms of number of moles as products. So because of that, I could assume that these are essentially concentrations in terms of my Q value. So it comes out to be 2.5 times 10 to the negative third at 2500 degrees Celsius. All right, so again, expanding on what we just talked about, if my temperature at 2130 degrees Celsius, this is my K. This is my K at 2500, okay? So as I increase the temperature, okay, of an endothermic reaction, what's going to happen to my K? Okay, so if I heat it up, it's going to shift it towards the right and make more product. So that means my K is going to increase. So since my K is increasing, this K value, probably the Q is less than K, okay? So this 2.5 is equal here, but we're at a much higher temperature, and the K would be higher at 2500 than this number here. So my Q is less than K. So what happens is I try to make more product. So it's going to shift towards the right and make more product. All right, so why don't you try this last one? You're trying to find the Kc and the Kp for this reaction. I will come back and show you the answers. All right, so there's a lot of calculation you have to do here to get to your final answer. First, recognize that H2 plus I2 goes to 2HI, that there's no change in delta N, so your Kc and your Kp are going to be exactly the same. So I could really focus on, since I was given grams, that I could convert them to moles. So over here on the right, I converted the H2, this is 0.0197 grams. I divided it by 2 to get to the number of moles. I2, I did exactly the same thing, and I get 3.6 times 10 to the negative third. So I plug them into my ICE table, and I have nothing of HI to start with. So this is minus x minus s plus 2x. But I was given something at equilibrium, essentially, or left unreacted. So I convert the grams, dividing it by 2, to get 6.9 times 10 to the negative third moles. So this is what I have left of H2. So when I subtract this from this, my x comes out to be 0.95 times 10 to the negative third. So that's my x. So 3.6 minus this number, I get a smaller number, 6.5 times 10 to the negative fourth. And then 2 times this number is about 5.9 times 10 to the negative third. 5.9 times 10 to the third. So finding my Kc here, because I have everything in moles, I have Hi on top and H2 and I2 on the bottom. So 5.9 times 10 to the negative third squared, 6.9 times 10 to the negative third, 6.5 times 10 to the negative fourth, you end up with 7.76. And again, like I said before, Kp is equal to Kc. Well, why can I use moles here when it's not molarity? Well, because the number of moles is the same on both sides, I could assume that it's all in the same container, that 1 liter, it's not going to be affected by that. So that is why you could do it in that particular case, because you have the same number on both sides. In most cases, I'm going to give you the number of liters that the container is in, or the reaction is in the container.